Hello again, Physics 20 Advanced Placement students. In today's lesson, we are going to talk about where the center of mass is located on both symmetrical and non-symmetrical objects, as well as with a system of particles, and then briefly talk about the connection between both the center of mass and center of gravity for an object. An object's center of mass is a specific point on a rigid body which represents an average location for where the total mass of an object is. So what this really means is if you looked at an object, if you could pick one point, and one point you could pretend like all of the mass is acting at that point, where would it be located? First of all, we represent the center of mass with a symbol that is, it's kind of like a little circle, put an X through it, and we shade the top part of the X, and we shade the bottom region of the X. And then we identify the center of mass with this point CM. So my center of mass is going to be one spot on my rigid object that has size where I'm going to pretend like all the mass acts. For the time being, we're just going to look at objects that have a uniform density, which means that if you were to take like on this rectangular box, like this section, and you determine its density, which is the number of particles that fit into that volume, and you took another section of the same volume, the same number of particles would be in that section. So one part of the box does not have a higher density than another one. So we're just going to focus on uniform density. If we're talking about symmetrical objects, I suspect your intuition is going to tell you you draw the center of mass at the geometric center. So a rectangular box, a circular disc, a thin rod, those are all objects with really, really nice symmetry. So if you were to pick one spot where you could pretend like all of the mass is acting, it would be at the geometric center. So that would just be at the exact center of all these objects. And again, we can represent that center of mass with that little circle symbol with an X in the top and bottom parts of the X shaded in. Okay, so geometric center. What happens if you have an object that does not have symmetry to it or has like a really, really weird shape? So I kind of drew like just this random blob shape. I mean, it kind of looks like a deformed bicycle seat in a way. Not so easy to identify where the center of mass is. Now you could probably make a guess as to approximately where it is, because I would just look to see, okay, where is most of the mass concentrated and make kind of like a guesstimate as to like where it is. But there's not really like an exact mathematical way we can determine this. But we can determine it experimentally. So if I wanted to experimentally figure out where the center of mass of this really weird shaped blob is, I could do the following things. One, take a string and you attach it to just any random end of the blob or that object. Then you hang the object from that point until it comes to rest. Somewhere below the hanging point is going to be where the center of mass is located. Okay, so what would this look like? So let's say we hang this funky shaped object from a string, and then it eventually comes to rest. The center of mass is going to be located somewhere directly below that string. So I could draw a line directly on my object that would show the center of mass is going to be located somewhere directly below there. Okay, so attach a string to a point on the object, hang it, wait for it to come to rest, and then we draw a line straight vertically downward. The center of mass is somewhere along that red line. Well, that doesn't tell me where the center of mass is. It just tells me a line I might find it on. So then we do this again. Repeat steps 1 and 2, but just do it from a different hanging point. So maybe this time around, we hang it from this edge. Let it come to rest. And once again, we would draw a vertical line straight down. Well, now I have the intersection of two lines. So if the center mass has to lie along the blue line and the red line, the only point where the center of mass could be is where they actually do intersect. So the intersection point of the two lines is where I would find the center of mass. So it'll be located directly at that intersection point between the red and the blue line. Okay, third one. So we've talked about symmetrical objects, non-symmetrical. What if we had a system of particles? So whenever we talk about a system, it's a collection of two or more objects. So my system in this situation is just two masses, M1 and M2. Now, for a system of particles, there's actually a center of mass for the whole system. So where would that be located in this particular situation? Well, first of all, let's say that M2 is bigger than M1. If they weren't, if M1 was the same mass as M2, then my center of mass location should just be halfway in between the two, which should be the midpoint of those two objects. But if M2 is bigger than M1, where would the system center of mass be? Well, the center of mass should always be where most of the mass is concentrated, so I would expect it to be a little bit closer to M2. However, we can actually calculate this exact point, unlike for that really weird deformed bicycle shape. Okay, we need to identify some quantities though. So first of all, we're going to identify x1 as being the position of mass 1 relative to some kind of a reference point, and we're using the reference point as 0 on a number line. x2 represents the position of mass 2 from that same reference point, which is 0 on the number line. To calculate the center of mass, we can use the following equation, which tells me that the center of mass for the system is equal to the sum of the mass of the object multiplied by its position divided by the sum of the mass of the system. Now, this looks a little bit weird just because it's in sigma notation, so we're going to expand this a little bit. If we expanded this, so sigma mx means you're going to take mass and multiply by position for every single mass in your system and then just add them all up together. Therefore, sigma mx would expand to m1x1 plus m2x2 plus m3x3 if you had more than two masses, but we'll just worry about the two we have here. Sigma m would just be the sum of all masses put together. What this equation is it's pretty much just a weighted average equation. So it's just accounting for the position of your mass and like how much mass is at that spot, and it just shifts the position accordingly based on where most of the mass is concentrated. So it's really, like I said, just a weighted average equation. Okay, in this equation, x represents the position of each mass from a common reference point, which is going to be the origin on a Cartesian plane or the number line you can see there. We'll do a calculation shortly to deal with that. Well, how about the center of gravity? The center of gravity is going to be important because in the next lesson, we're going to start to draw free body diagrams of rigid bodies. So a center of gravity is one point on the rigid body where you can pretend like the force of gravity is acting. Okay, so even though a rigid body, like every individual particle would have the force of gravity acting straight down, the center of gravity would just be one spot where we can draw a force of gravity vector. We identify this on a diagram with the symbol that's a little bit different. So instead of doing an X for the center of gravity, what I would do is I would do like a cross, kind of like a crosshair. Then you shade in the bottom left region, and then you shade in the top left, top right region, and we label that as being CG. One note, the center of gravity and center of mass locations should be the same like 99% of the time. In fact, if you're in a uniform gravitational field, so what that means is if your object is in a gravitational field and every point in that object was in a gravitational field with a magnitude of 9.81 newtons per kilogram, then the center of gravity location is the same as the center of mass location. However, let's look at this situation. So I've drawn some gravitational field lines for a rigid body that's in a non-uniform gravitational field. So just a quick recall in regards to field lines. If the field lines are more spaced out, it means the field is weaker there. If they're closer together, it means the field is stronger. So what this diagram is trying to show is that on the left-hand side, the gravitational field is weaker. On the right-hand side, the gravitational field is stronger. So where would the center of gravity location be? Well, it'd be more shifted towards the region where the field has a stronger influence. So maybe be somewhere located just to the right side of where the center of mass would be. The center of mass is still located in the same direction. The center of gravity would be different just because the force of gravity is different. And just remember, to calculate the force of gravity, Fg would be equal to m times g. So if g isn't a constant, you'd have to shift it towards where g is larger. Again, we're not going to have to worry about this mathematically. It's just simply one note. I mean, like, if you're looking at a common object, like, it's not going to be in a non-uniform gravitational field. If I have a water bottle on my desk right now, the whole water bottle is subjected to the same, the gravitational field strength in that region is the same thing. I already identified that. So I said in the non-uniform gravitational field shown below, where would you expect a center of gravity to be located relative to the center of mass? It'd be shifted more towards where the center of gravity has the stronger, or the gravitational field is stronger. Okay, so let's do a couple of examples. So it says in each of the systems of particles shown, so we have system 1, which is a one-dimensional type problem, and system 2, which is going to be a two-dimensional one. I want to A, calculate the position of the center of mass, and then 2, sketch the location of the center of mass position. All right, so first of all, let's identify the position of these objects. So this one will be x1. And we'll say this is the number line, it says centimeter grid paper. Okay, so this would be positive 2 centimeters. And then this one would be 1, 2, 3, 4, 5, 6, 7, 8. I think we're at positive, I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have x2 would be equal to positive 10 centimeters. Okay, so I want the center of mass location for the system. We've already identified if M2 is bigger than M1, which is what it's stating here, it's going to be a bit more shifted towards M2. So my center of mass equation looks like your x center of mass is equal to the sum of all your masses multiplied by your positions divided by the sum of the mass for the system. Okay, so this would expand to M1, x1, plus M2, x2, then divide that by the sum of the mass, which would be M1 plus M2, and now we can just plug numbers in. M1 has a mass of 3.0 kilograms. X1 is positive 2 centimeters, plus M2, which is 6.0 kilograms, times its position. X2 is at 10 centimeters. And then divide this by the system mass. So that'd be 3.0 kilograms plus 6.0 kilograms. All right, so that would be 2 times 3 is 6 plus 60 divided by 9. So I think we should get a number of about positive 7.3 centimeters. Okay, so we're going to draw this, the center of mass location. Okay, so 1, 2, 3, 4, 5, 6, 7. So it'll be 1/3 of the region in here. So draw a little circle as best you can. And then for the center of gravity, that's one where we draw the X. Center of mass is where we draw the X. And then we can just label that as CG. So yeah, That's of course we predicted. The center of gravity should be more shifted towards the heavier mass. Okay, this one's a little bit more complicated. The only reason it's a bit more complicated is because you have a two-dimensional plane as opposed to just a one-dimensional number line. Okay, so what we're going to do is we're going to need to calculate an ordered pair for the center of mass location. So we're going to want to figure out the x center of mass coordinate and the y center of mass coordinate. So to do that, we're going to need to identify two things for each of these masses, both its x coordinate and its y coordinate. Okay, so for this guy, your x coordinate, x1, relative to the origin would be 1, 2 to the left, so that's going to be negative 2 centimeters. And then its y coordinate, y1, is going to be equal to, well, it's located up by 6, you got positive 6 centimeters. This one, you'd have x2 would be equal to, it's located at positive 4 centimeters, and then you don't have a y coordinate. Well, you do have a y coordinate, it's just 0, because you're on the x-axis. Okay, so it's going to be located somewhere between the two of these guys, and it's going to be located closer to M2 just because M2 is the bigger mass. Okay, so we're going to do two separate calculations. So first of all, we'll calculate the x center of mass. So the x center of mass would be equal to the sum of, take all the masses and multiply by their positions. So m times x divided by sigma m. So this would then be equal to m1 x1 plus m2 x2. And then we'll divide this by sigma m, which is m1 plus m2. Plug the numbers in now. So m1 is 3.0 kilograms. Multiplied by x1, which is negative 2 centimeters, plus m2, which is, I think it's double the mass, so 6.0 kilograms. Multiplied by its position, which is positive 4 centimeters. This top and some set of brackets. Divide this by the sum of the mass for the system, which would be 3.0 kilograms plus 6.0 kilograms. Okay, and your x center of mass coordinate should be equal to positive 2.0 centimeters. Now we also need the y coordinate for the center of mass because we're dealing with a two-dimensional plane. So I can just take the same equation except just replace x with y. So then I would have the y center of mass would be equal to the sum of the masses multiplied by their y position divided by sigma m. So this would then turn into m1, y1, plus m2, y2, and divide this by m1 plus m2. Plug the numbers in now. m1 is 3.0 kilograms. Multiplied by, we can actually get rid of this term here because y2 is 0. Okay, so that'd be 3.0 kilograms multiplied by y1, which is positive 6 centimeters. And then divide this by the sum of the mass. 3.0 kilograms plus 6.0 kilograms. And then this would give me the y coordinate for the system center of mass would be equal to, it's also positive 2.0 centimeters. Okay, so let's sketch this now. So it's going to be located at 2, 2. So 2, 2 would be located right here. Draw a little X to represent the center of mass, shade in the top part, shade in the bottom part, and then we have CM. Again, CM is the center of mass. And I can see, if I drew a straight line from M1 to M2, the center of mass is located closer to the heavier mass, which is what it should be. Oh, by the way, I just realized here that I did CG. That should be CM. I mean, CG would also be at that same location, but it does specifically say the center of mass. So let's do CM. Okay. So that's it for this lesson. So in the rotational motion workbooklet, there is one problem. I think it's an old AP exam question, a multiple choice question, where you can do a quick system center of mass calculation. And also there is a lab that you can do. Now, all you need to do to complete the lab is you need just a piece of cardboard, you need some string and some tape. And it involves just making a mathematical prediction as to like where the center of mass is on an L-shaped piece of cardboard, and then also confirming that by doing the experimental procedure of hanging with strings and drawing lines and looking for the intersection point. And then in the next lesson, we're going to talk about a very important physical property related to rotating objects dealing with torque. And I will talk to you then.